Lesson 16, we're looking at the margin of error when estimating a population proportion. Okay. Students use data from a random sample to estimate a population proportion. Students calculate and interpret the margin of error in context, and students know the relationship between sample size and margin of error in the context of estimating a population proportion. Now, let's look and see what all this is actually telling us here. When we're talking about margin of error, we're saying how far off we could be with our estimation. Okay, so suppose there's a mystery bag that has chips in them. If you know that there are red chips in the bag, how would you find the proportion of the red chips in the bag? And that's what this whole lesson is going to be looking at. And we're going to be looking at a lot of reading and a lot of answers that not really calculating anything. We're just really figuring out how to estimate when estimating a population proportion, what the margin of error may be. So there's another one of those lessons where you're going to have to use your imagination. All right? We're doing an exploration or an exploratory challenge for exercises 1 through 4. We have a mystery bag. It says in this lesson you will use data from a random sample drawn from a mystery bag to estimate a population proportion and learn how to find and interpret a margin of error for your estimate. So it says write down your estimate for the proportion of the red chips in the mystery bag based on the random sample of 30 chips drawn in class. All right, so what do you estimate? You can go ahead and write that down. All right, it says let's say that I drew 10 red chips out of 30 samples. So what would you say the proportions is? Okay, if I drew 10 out of the 30, what would you say that the proportion would be? Okay, hopefully you're thinking that's going to be about 1/3. Let's look. Tanya and Raul had a paper bag that contained red and black chips. The bag was marked 40% red chips. They drew random samples of 30 chips with replacement from the bag. So took one out, put it right back in. They were careful to shake the bag after they replaced a chip. They had 9 red chips in their sample. They drew another random sample of 30 chips from the bag, and this time they had 12 red chips. They repeated this sample process 50 times and made a plot of the number of red chips in each sample. A plot of their sampling distribution is shown below. So this is not the proportions, but this is the number of red chips that they have pulled out. So out of their 30 samples, this is how many red chips they pulled, and they did that 50 times. Okay, so there's going to be 50 of those dots because they did it 50 times. So what was the most common number of red chips in the 50 samples? Does this seem reasonable? Why or why not? Okay, so I think we can say that 10 was obviously the most. Now, does this seem reasonable? Well, the most common number was 10 red chips, which seems reasonable because we expected to have about 40% successes. And 40% of 30 is 12 successes, and 10 is close to that. Remember, these are just estimates. So what they're saying is we had 40% was supposed to be red chips. That's what our question told us. So if we're only pulling 30 chips at a time, what's that going to give us 40% of? Or what is 40% of that? And they say that that is 12. So 10 is not that uncommon. That is a reasonable explanation. Now, if you had like a 2, then no, that's not reasonable. If you had 28, then you would say, obviously, that is not reasonable if the bag was marked to have only 40 red chips. Okay. So what number of red chips, if any, never occurred in any of the samples. Okay, so you would have to draw this line right here and say what's below that and what's above that. Well, they never got a sample with a number of red chips less than or equal to 6 or more than or equal to 20. Okay, there was never any samples that had that many chips in it, red chips. So given an interval that contains the likely number of red chips in the sample size of 30 based on the simulated sampling distribution. Okay, well, we could say that there would be from 7 to 9 red chips. That would be an interval, right, of having likely red chips. Now, it says do not focus on exactly what likely means. The object is to see if it is at all reasonable for any outcome to occur by chance. So so it's basically saying don't look and see what is most likely. Okay, is it likely that you could have an interval of 15 to 18? Sure, because we have 15 to 18 here. Okay, it could happen. It is likely to happen that you would have a sample of 15 to 18 red chips. Now, do you think the number of red chips in the mystery bag could have come from a sample drawn from a bag that had 40% red chips? So why or why not? Okay. This says this depends on the number of red chips that were observed in the random sample drawn from the mystery bag. If the observed number of red chips was 18, the answer would be yes, because 18 red chips occurred just by chance in the simulated sampling distribution. So, some students might suggest that 18 or more red chips only occurred twice in 50 random samples. So, it was not too likely, but could happen by chance. The important concept is that students look at the simulated distributions to see where the observed outcomes fall in respect to that distribution. So, yes, it is likely that it came from a bag of 40 because it did happen in our samples. Okay? Page 3. It says 9 different bags of chips were distributed to small teams of students in the class. Each bag had a different proportion of red chips. Each team simulated drawing 50 different random samples of size 30 from their bags and recorded the number of red chips for each sample. The graph of their simulated sampling distributions are shown. So what it's saying is we have 30 chips in the bag and we're going to pull 50 times. We're going to do 50 different random samples of size 30. Okay. We're pulling 30 chips and we're going to do that 50 times. Okay. That's what that's saying. Not that there's 30 chips in the bag. It just means we're going to pull 30 chips out, record our data, so whether it's red chips or not, and then we're going to do that 50 times. So here are the results. So this shows that there's only 10% of red chips. And it's very low down here. Okay. And it should be because there's only 10% of red chips. Well, what's 10% of 30? Well, there should be only 3 red chips in there. Now, 10% of 30 would be 3 red chips. So there's no way that you should draw 20 red chips whenever there's only 3 in there. Okay. That should not happen. Okay. And I do know that you are putting it back in there, replacing it each time you've drawn it, but you still should not have pulled 20 out of 30 red chips when there's only 3 in there. Okay, so and then you can look at each one of those. You can see how it progresses more from 0 up to 30 as the population percentage increases in those chips. Now, let's look at number 3. It says think about the number of red chips in the random sample size of 30 that was drawn from the mystery bag. Based on the simulated sampling distributions, do you think that the mystery bag might have had 10% red chips? Explain your thinking. Okay. Well, if the random sample size of 30 from the mystery bag had 18 red chips, the answer would be no, because 18 never showed up in all of the samples. Okay, so there's not going to be any example there where you would come up with 18. Okay, 10% red chips, no way you're going to get 18. No way. Now, this says based on the simulated sampling distribution, which of the percentages, 10 to 90%, might reasonably be the percentage of red chips in the mystery bag. Okay, so this means if you got 18 red chips, which ones would be likely? Well, let's look. 10 and 20, we didn't get 18. 30 is getting close, but we still didn't have 18. 40, we have 1. So is it likely? Yes, it is likely. It could happen. Here we have some for 18. Here we have some for 18. Here we have, oh, that's not right. Here's one for 8, or some for 18. Here's one for 18. And there's not one for 18 here. So what you would say is, what might be reasonably be the percentages? Well, if the number of red chips in the sample of the mystery bag was 18, it looks like just by chance the sample could be drawn from the population of having 14, so from 40% to 80%. And that's what we said. Here's 40%, 50% works out, 60% works out, 70% works out, and yes, 80% there was by chance of drawing 18%. So that would be your interval basically. Okay. Let's look at page 4. Let P represent the proportion of red chips in the mystery bag. For example, P is equal to 0.40 if there are 40% red chips in the bag. Based on your answer to part B, write an inequality that describes plausible values of P. Interpret the inequality in terms of the mystery bag population. Right. So we would say 40 hundredths is less than or equal to P, which is less than or equal to 80 hundredths. Okay? Or we would say P is greater than or equal to 40%, and P is less than or equal to 80%. This means that based on the simulated sampling distributions, the true proportion of red chips in the mystery bag could have been anywhere from 40 hundredths to 80 hundredths. It would not have been surprising for a random sample of size 30 drawn from any of these populations to have included 18 red chips. Remember, likely just means that it could happen. Okay? And the inequality, like the one you described in part C of the exercise 3, went from 30 hundredths to 60 hundredths. It is sometimes written as 0.45 plus or minus 15 hundredths. The value of 15 hundredths is called a margin of error. The margin of error represents an interval from the expected proportion that would not contain any proportions or very few proportions based on the simulated sampling distribution. Proportions in this interval are not expected to occur when taking a sample from the mystery bag. Write an inequality you found in exercise 3, part C, using this notation. What is the margin of error? Well, we said from 40 to 80. So what we would say is 0.60 plus or minus 0.20. Okay. So using only 18 as the number of red chips in a random sample from the mystery bag. That was exercise 3 part, well, that was just exercise 3. The interval would be 0.60 plus or minus 0.20. The margin of error defined as an interval of 20 hundredths. So here's your margin of error. Okay. So I just want to go back and show you on those graphs. Okay. So we're saying that it's probably going to be population of 60%, but it could be as low as 40% and as high as 80%. Notice that 60 here has the center of the pigs as 18. There's a lot to the right of it and a lot to the left of it, and that's what it should be. Okay. So that's all you needed to know for that margin of error part. Let's look at Exploratory Challenge 2. And this will be for exercises 5 through 7, where we have a samples of size 50. Okay.